Thank you everyone for attending this talk. This is joint work with Alisa, Chang, Badih, Ghazi, and Ravi, Kumar. We study clustering problems. In its general form, the clustering problem can be stated as follows. We are given a set X of n points in R to the D, and our clustering algorithm would like to output a set of centers that well represents the point. There are multiple ways to define how well the output centers represent the input points. In this work, we focus on the so-called k-means objective, where we would like to output k-centers that minimize the sum of the square of the distance of each input point to its closest center. For the purpose of achieving additive error in differential privacy, we will also have to assume that the input points belong to the unit ball, which we denote here by BD. There are two popular models in differential privacy. The first is the more relaxed central model, where the clustering algorithm is allowed to see the raw input points. And the only restriction here is that the output set of centers is differentially private. The second model of differential privacy, which is the main focus of this work, is the so-called local model. In this setting, we think of each point as being held by a user. And the user can, given this point, send a message or multiple messages to the algorithm, who then process these messages and output the set of centers. Here, we would like the set of messages sent by each user to be differentially private. Note that the local model is more stringent and it requires less trust in the central authority because everything sent by the user is already differentially private. Now that we have defined the problem and our models, we can now describe the results in previous works and also our paper. The k-means problem is well known to be NP-hard, and thus people have focused on studying approximation algorithms for the problem. When there is no privacy constraint, the best known approximation ratio is currently roughly 6.36 by Ahmadian et al. In the central DP setting, Kaplan and Stemmer gave an approximation algorithm that achieves constant approximation ratio. However, this approximation ratio is very large, and by our estimate is more than 100. So last year, we gave an algorithm that improved on this approximation ratio. Specifically, our algorithm can achieve approximation ratio arbitrarily close to the non-private algorithm. And as usual, differentially private algorithms have to pay in terms of additive error. And in this case, both our algorithm and the Kaplan-Stemmer algorithm incurs an additive error of polynomial in the dimension times k times log n. Unfortunately, the algorithm from our previous paper only works in the central model and not in the local model. And for the latter, the previous best known approximation algorithm is that of Stemmer, who gave an algorithm that achieved a large constant factor approximation. Furthermore, his algorithm requires several rounds of interaction, and he posed as an open question whether this interaction is necessary. In this work, we answered his open question by showing that, in fact, there is one round local DP algorithm that can achieve not only a constant approximation ratio, but also approximation ratio arbitrarily close to that of the non-private algorithm. More formally, if there is a non-private algorithm with approximation ratio W star, then we can give an epsilon non-interactive local DP algorithm that achieves an approximation ratio W star times 1 plus gamma for any constant gamma greater than 0, an additive error that is an order of square root n times poly of dk times log n. And note here that Stemmer showed that this square root of n factor in the additive error is necessary. Now that we have stated our main result, let us now dive into the main algorithmic ideas of our work. At a very high level, we follow the framework in our previous paper, which was mainly designed for the central model. This framework consists of 3 steps. The first step is to do random projection in order to reduce the dimension of the data set. Once we are in this low dimension, we then identify the K clusters in the low dimension, which is typically easier than doing the same thing in the high dimensional space. And with this clustering in mind, we go back to the high dimension original space and then compute the center for each cluster. With the high level overview of our algorithm in mind, let us now dive deeper into each part of the algorithm, starting with the dimensionality reduction step. Here, we appeal to a recent breakthrough result of Makarishev, and Rachenstein, who show that if we randomly project the points into roughly log k over gamma square dimensions, then any good approximation in this low dimensional space is also a good approximation in the high dimensional space as well, where the approximation ratio gets multiplied by only a factor of 1 plus order of gamma. In other words, this means that our job now reduced to just finding a good approximation in this d prime, which is roughly log k dimensional space. Okay, so now we are in this low d prime dimensional space. So how do we cluster the points in this low dimensional space? What we can show is, in fact, a local DP algorithm that can produce a private core set of the input set. And just to recall what a core set is a set of points y such that for any set C of k centers, the cost of y with respect to C is roughly the same as the cost of the input point set x with respect to C, up to some small multiplicative and small additive errors. And note here that the additive error we can achieve is square root n times poly k times exponential in d prime. But this exponential in d prime factor is okay because we are now in log k dimension. So this factor is only also just polynomial in k as well, and we are okay with that. So the detail of how we construct this core set will be described in the next slide. But once we have this core set, it's very easy to get the cluster. Since the core set itself is already private, we can just run any non-private approximation algorithm on this core set, and that will give us a W approximation clusters C1 so on to CK of these low dimensional point sets. That's great. So now we only have to specify how we construct this private core set. To do this, we use a modification of a data structure due to Harpelet and Mendel called the net tree. So the net tree represents a hierarchical partitioning of the space, where we start off at the root with the entire ball, and then we partition further and further as we go down the tree. More specifically, at each node, we put a net on that partition, and each point in the net defines the smaller partition in a child. And note here that the number of children of each node is exponential in the dimension d prime because we are putting a net on the partition. However, as stated in the previous slide, this exponential in d prime is only polynomial in k, so our algorithm is still efficient. Okay, so with this net tree, how do we construct our core set? So we construct our core set by exploring this net tree carefully. We start at the root, and then at each level, we will explore tau nodes with the largest number of points, where our tau here is something like polynomial in k times exponential in d prime. And once we finish this exploration, at each node that is explored, we put one representative in the core set with appropriate weight. So this algorithm doesn't quite work as is in our setting. And the reason is that this algorithm is very iterative in nature, whereas we would like our algorithm to work in the non-interactive local DP setting. Seemingly, if we try to use this algorithm directly, we would have to iteratively go step by step and explore each level, where we will require one interaction in each step. Fortunately, however, we can use sketching technique to overcome this problem, because we can use sketching to estimate the number of points in each node, which already suffice to implement this algorithm. And the sketch itself can be created directly without the knowledge of the nodes explored beforehand. So this can be done non-interactively. And that's the high-level ideas of our core set construction. Of course, we have to handle noise added both by the sketch and also by differential privacy. And this is one of the reasons that we incur that square root n additive error in the end. Okay, we are now in the last step of the algorithm, where we would like to compute the corresponding center in the high dimensional space. So if we were not restricted by non-interactivity, this would be very simple. We could just spend one more round to average up all the points in each corresponding cluster. However, we cannot do this because we want to do everything in a single round. However, observe here that the k-mean center of each cluster is simply the average of all the points in the nodes in the net tree mapped to that partition. This means that we can once again use the sketching technique to overcome the aforementioned problem, specifically using sketching together with a local DP algorithm by Dushi et al. To compute the sum of vectors. We can once again compute the estimate average of points assigned to each node explored in the net tree. Once we have this, the estimated cluster center is simply the weighted average of this average. And that's it. That's basically all the main ideas in our algorithm. To conclude here, we have presented a one-round local DP algorithm for k-means, which achieve approximation ratio arbitrarily close to any non-private approximation algorithm, and incurs an additive error of square root n times polynomial in dk and log n. In our paper, we also show that using basically the same framework, we can also get a clustering algorithm in the shuffle model, which is a more relaxed model of differential privacy compared to the local model, but more stringent compared to the central model. In the shuffle model, we once again get approximation ratio arbitrarily close to any non-private algorithm. And furthermore, the additive error in the shuffle model is only polynomial in d times k times log n. And note here that these guarantees roughly matches the guarantee in the central model. In other words, these results subsume the result for k-means in our previous papers. In terms of open question, in our previous work in the central model, we also showed that the framework, this three-step framework, applies not only just for k-means, but for other clustering problems. However, we do not know yet how to make the algorithm for those problems work in the local model. Specifically, these problems include the k-median problem, in which the objective is the same as k-mean, except that now is the sum of the distance to the closest center instead of the sum of square. And the densest ball problem, where we are given a target radius r, and we would like to find a ball of size roughly r that contains as many points as possible. For both of these problems, the best known approximation ratio in the local model are still constant but large constant factor approximations. In the case of k-median, the additive error is roughly square root n, but for densest ball, the additive error is n to the 2/3. It would be interesting to see whether we can get tight approximation ratio for these problems in the local model, and whether we can do those in one round. And for densest ball, since the additive error is n to the 2/3 at the moment, it would also be interesting whether we can get it down to square root k as well. And with that, I would like to conclude this talk. Thank you all very much for your attention.